you. So this year's some distinguished lectures is by Professor Maxim Kontsevich. Probably he's so famous for working without reading introduction. He's a professor at IAGS class. He has several prizes. I cannot name all of them. Include one. One of them is very clever. Okay, so today's first lecture one is not mathematics.
Okay, thank you very much. And this lecture will be elementary. I think for participants of a conference will be nothing new, but maybe you'll still enjoy. And also I tried to make, I had a jet lag and woke up very early in the morning and decided, why don't I make experiments and to learn the thing which my colleague physicists do, PowerPoint presentation. 200 pages, yeah. I made about almost 70 pages, and I can say never again, yeah. But okay, but we'll see what came from my experiment, yeah. Yeah, so this is about what is tropical mathematics, and we start with the usual algebra. In usual algebra, we have some operations on numbers. Addition, yeah, everybody knows, plus subtraction, minus multiplication, times, and division. Yeah, but division is not really always defined because you cannot divide by 0. Yeah, so it's something secondary to multiplication, but it's not always divided. So we forget about division, get just three operations. Okay, and they satisfy some rules or axioms. So multiplication is commutative, associative, and division is related, subtraction is related to addition. Okay, then we get similar things for multiplication, commutativity and associativity. Then there is a distributivity law. Hope I didn't make any mistake yet. Okay. And I just forgot, there are two special symbols, 0 and 1, which are trivial for respective for addition and the multiplication. And from this you can extract that any number times 0 is equal to 0. It's a corollary of all these things. Okay, so it's very, very familiar things to everybody. Now, what is tropical algebra? And again, it could be kind of numbers. And we remove one subtraction. We have just two, addition and multiplication. And we have actions which are very similar to what we have for usual numbers. Addition is commutative and associative. You have 0. Multiplication is commutative and associative, and you also have 1. But now, because there's no subtraction, I have to add by hand that any number times 0 is 0. Also I have distributivity law. And then I get this funny new axiom. Any number added to itself is equal to itself, which is definitely wrong for usual numbers. Yeah. So it doesn't hold from usual numbers. And now one can compare two worlds. So what I said, usual algebra in kind of more scientific ways, is speak about commutative associative rings. And in tropical algebra, we speak about commutative associative semi-rings because there's no subtraction, and also idempotent, which was this funny axiom that a plus a equal to a. Okay, what is the simplest ring which is kind of contains in everything in any other ring, or maps to any other ring, is the ring of integers. From minus infinity to plus infinity, all integers map to any ring. And the simplest idempotent semi-ring has just only two elements, 0 and 1. You can imagine the only thing which you can remember is 1 plus 1 is equal to 1 in this world. And for example, now consider Newton binomial expansion. Let's take A will be variable in some ring or semi-ring, and consider 1 plus A and consider powers of this guy. So in usual algebra, we have binomial coefficients. You see, we can take square with coefficients will be 1, 2, and 1, then 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. But in tropical algebra, it's much simpler. All coefficients are equal to 1, because 1 plus 1 equal to 1, and it's equal to 1. Yeah, okay. Now, so you see, it's kind of much easier to do calculations in tropical algebra. And what is the most important, in fact, example of tropical ring, or in a certain sense, is the following one. So this ring consists of infinitely many elements, which I will denote as the usual numbers: 0, 1, 10, 100, 1,000, million, trillion, and all powers of 10. And the tropical multiplication is just the usual multiplication. If you count 3 zeros, 1, 10 to the power 3, 10 to the power 5, and then get 10 to the power 8. Good. And what is tropical addition? It's the usual maximum. You add 1,000 plus 100,000 to get 100,000. But it's, of course, it's wrong. We know that 100,000 plus 100,000 is 100,000, 101,000. But it's not very far. Yeah, so you see that's almost true fact. Yeah, so it's, yeah, and yeah, sure, yeah. No, in fact, it's if you deal with some kind of big things, it's how you count. You don't keep track on details, yeah. Yeah, so if, in all this, I think it's convenient to replace powers by logarithms. I'm cheating a little bit because there was also number 0, and logarithm of 0 is minus infinity. But 0 is this minus infinity, one can always forget about them. It's okay. And then after this replacement, the tropical addition will be the usual maximum. And tropical multiplication will be the usual sum. And then if you make this reformulation, your separations are not tropical addition, tropical multiplication, but maximum sum, you get something called max plus algebra. And how this subject was named originally, and why is the name tropical? Kind of funny name. But first one can ask, for example, what is ring for ring? Is it something round? I don't know. It's a really bizarre name. And tropical is the same bizarre, meaningless, completely meaningless name. One of the explanation is that it's named after, I forgot the name of some Hungarian applied mathematician, so kind of computer scientist, who is working in Brazil. Yeah, so it's, and he uses for operational calculus and so on. Yeah, in fact, there are many, many origins. The subject it's actually probably very, very old. I heard from Sir Michael Atiyah that, in fact, it was created by Arabs who invented algebra, but then at some point it some kind of degenerated, and nobody was interested what they're speaking about, because they reduced to this idempotent rules. Yeah, and for a while it was kind of unclear what is going on, but now we understand they invented at some point tropical algebra. But I think what is the real origin for this name is it's actually a very good excuse to make conference in some nice places. Yeah, so if you like palm trees and so on, yeah. Yeah. Now, sometimes there are conferences in Nordic countries, just only, but only for fun. Yeah, it's a joke. Yeah, yeah. Essentially, I think it's called tropical exactly for this. Yeah. Okay. 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 What is tropical algebra is good for? it's a kind of extremely useful tool when one deals with very big or very small numbers, or to get, have somewhere some big numbers or small numbers and understand kind of qualitatively what's going on. So here's an example which I solved on my computer to prepare this talk. Let's consider equation of third degree with some coefficients that are small, like first coefficient is 1 over 1,000, but next coefficient is 1,000, then 100, then 1. Yeah, so it's the coefficients going up and down. Yeah, so this equation, and we want to see what are solutions for this. Fortunately, it has 3 real solutions. And I draw with many, many digits all the 3 solutions. So the first, of course, all solutions are negative because the equation has positive coefficients. There's no positive real solutions. And the first, I think it's minus 88, which we say now it's tropical mathematicians. It's minus 100, yeah, so we replace all kind of approximately. The second, it's 11, it's even closer, it's minus 10. But the third one, it's 1 over million, and you see it's extremely close. If you just look, it's the precision is really huge. Okay. Yeah, so we get this 3 powers of 10, 2, 1, and minus 6. Somehow they come from this equation, and the question in which way? Yeah, so this equation has a tropical version. Because what we do in tropical geometry, if we consider sum, we replace by maximum. And then we consider product, we replace by sum. And then you see what is going on. I get sum of 4 terms. And I take maximum of 4 expressions. You can think about small x as logarithm of capital X. So the first term is 1 over 1,000, and it's 10 to the power minus 3, so we write minus 3. The second, 1,000 times x, it's 1,000 10 to the power 3, and x, capital X, is 10 to the power small x, so we write 3 plus x. Then the third term will be 2 plus 2x, and the third term will be 3x. So we consider function on, we have 3 linear functions. And instead of writing equations that something is equal to 0, algebra, one does the following. One try to find small x such that maximum is achieved at least twice. Because if one term is larger than another, then the thing cannot be equal to 0. This one monomial will be much larger than the rest. So we have this condition that maximum is achieved twice, and now one can see it. One consider function. Should draw 4 linear functions, minus 3, 3 plus x, and blah, blah, blah. So the 3 red lines that take kind of things which goes around. You get things with 4 intervals of linearity, and you get 3 points, 3 breakpoints, which has coordinates. If one, I didn't write actually scale here, but they break exactly when x coordinates is equal to minus 6, 1, and 2. And if you remember, this minus 6, 1, and 2 were exactly exponents of roots. Yeah, so that's how, using tropical geometry, you can see approximately, solve approximately algebraic equations. Yeah, so it's actually great progress, because in algebra, you can solve quadratic equations using radicals. There are complicated formulas for equations of degree 3 and 4, no radicals for equations of degree 5 and higher. But here in tropical algebra, one can see solutions kind of immediately. Yeah, so it's really much easier. So I kind of recommend everybody to move to this route. Yeah. So it's a bit... Okay. Now I go to really the heart of the talk, equations for planar curves. So I will compare picture in usual geometry and in tropical geometry. So first, let's write equation for a line. It has 2 coefficients, a and b, capital B, you can write as ax plus by plus 1 equal to 0, get some straight line, any line, except maybe passing through 0 can be written like this. And in tropical geometry, what we say, we consider function of, we have three expressions depending on x and y. A, B are parameters for our line. And we wanted, among three numbers, a plus x, b plus y, and 0, the maximum is achieved at least twice. And what you get? You get this strange beast consisting of three rays. And if you change parameters a and b, you just make parallel translation of this tropical line. Any two tropical lines intersect at exactly one point. Because it's really wonderful. Just move second line here, here, here. Yeah, so they also intersect at one point. But not exactly always. Yeah, they can intersect by the whole ray. Of course, if they coincide, they intersect by three rays. Yeah, so there's not everything goes as smoothly as in real life, but very close to it. And for example, you can take your favorite theorem from projective geometry, like Pappus theorem. What is Pappus theorem? You take two lines, which are black here, took 3 points on these lines, and connect each point with two kind of other points on another line. You get six new blue lines. They have some new intersection points, and they lie on one line. Okay. And then it has a tropical version, but I was lazy enough not to draw it for you. It will take for me weeks, I suppose. Yeah, really, it will be some kind of fantastic picture with this many. You can imagine here how many lines. We have something like 9 lines, but each line will consist of 3 rays, so we'll get 27 rays. Yes, so it will be kind of some kind of nightmare. Okay. Yeah, but now we can consider equation of second degree. So we consider quadrics, like ellipse or hyperbola, just draw ellipse. And in tropical geometry, we get slightly more funny curve. As in real quadrics are actually of different shapes. There are ellipses, there are hyperbolas, and there are empty curves. And also in tropical geometry, there are I don't know, something maybe about 5 different tropical curves. One is kind of the most symmetric one, which is analog to ellipse. And if you consider quadrics, then it intersect lines. Quadrics intersect lines in 2 points. It's a kind of Bézout theorem. And here you see it's the same. Yeah, so it's. And if you move line whatever you want, it's always will be 2 intersection points. And if you make this funny quadrics, it's also will be 2 intersection points. And actually, see, it's kind of better because in real geometry, sometimes line do not intersect quadric. But in tropical geometry, it's always, yeah. So it's really great advantage. Yeah. So but we know when quadrics intersect lines, always we should go solve equations in complex numbers. Then any, for example, equation of degree n has n roots and so on. So in complex algebraic geometry, we have kind of ideal situation when quadrics intersect lines. And tropical geometry, in a sense, is very closely related to complex world, not to real world. Although we draw kind of real pictures, they're secretly about complex numbers or some algebraically closed fields. Now, one can go draw cubics. Yeah, I draw just one of typical real cubics, which consist of 2 components. And in tropical geometry, you see now even more complicated. This again, I just draw some kind of most symmetric representative, and it's no longer a tree. Before we have a tree for lines and quadrics. We have just trees, but here we get a graph with one loop. And what does it say? It says, so, in fact, if you go solve question complex numbers, the complex line is a real plane, because complex number has a real and imaginary part. And real plane is sphere minus 1 point. Okay, and now if you consider complex affine quadric, it's topologically a cylinder, which is again sphere, but now minus 2 points. And now we consider affine cubic, it's a torus minus 3 points. So we consider curves of surfaces of more complicated, first to spheres, then torus, and then will be eventually surface of with 2 handles and so on. And we remove gradually more and more points, 1, 2, 3, and so on. And tropical line is sphere minus 3 points. I'll explain it in a second. Tropical quadric is sphere minus 6 points. Tropical cubic is torus minus 9 points. So you remove 3 times more points than in usual geometry. Yeah, so that's kind of small picture. How one can think about tropical curves as surfaces. Yeah, I recall that tropical line is consists of 3 rays, but you can thicken them a little bit and get three half cylinders, and then together you get a topological sphere with 3 punctures. And this is a picture of tropical quadric, which is sphere minus 6 punctures. And this is a picture for the tropical cubic, which is torus minus 9 punctures. Yeah, so you see that this cycle in the graph represents a genus of a curve. Why number of punctures in tropical geometry is 3 times more than a number of punctures in usual geometry? In usual algebraic geometry, we consider complex algebraic geometry. We consider a curve in C2, which is complex projective space minus complex projective line at infinity. And then if you have curve of degree d, then it intersects this line at infinity exactly d points. But now in tropical curve, kind of secretly sits in C star square, which is CP2 minus CP1 and plus another CP1 and another CP1, which are coordinates axis. The coordinate axis, and this curve sinks at infinity. So you get actually, you have 3 divisors removed, and now each curve, generic curve of degree d intersect these divisors at 3 d points, but each of them intersect at d points. Yeah, so let's explain this in 3. And then one can play with this a lot. One can draw many planar tropical curves, and then you get actually not curves, it's kind of graphs consisting of straight intervals, and each interval will have natural length element, so it will be kind of natural vector of speed. And as you notice, all these graphs are kind of like eagles. They have edges go in kind of all possible directions. There's no kind of convex in this thing. And the reasons why they should go in cannot really lie in half plane is it's a balancing constraint. For any vertex, you have finitely many edges coming to this vertex, so you get a bunch of vectors in, let's say, plane, and the sum of these vectors should be equal to 0.
What are the speeds?
No, I claim that there are natural speeds. The natural length element on it's a bit long story. Yeah, it's not just picture, but it's actually kind of thickness of the picture. There is some length elements, and this allows to speak about vectors. Vectors will be integer vectors. Vectors with integer coefficients. Okay. And what are high-dimensional tropical objects? Or varieties. One can say that piecewise linear, some gadgets, or something, describing the shape of a complex algebraic variety which depends on a small parameter and degenerates badly in some sense as parameters goes to 0. Maybe I just give you a hint of possible definition, what is going on. A possible definition of tropical variety is the following. First of all, one can speak about tropical hypersurfaces. In Euclidean spaces, namely, you pick a bunch of linear affine functions. Okay. And focus points the maximum of f1 of point P is achieved at least twice. So then I can speak about hypersurface. It will be kind of high-dimensional generalization of these pictures you have drawn on a plane. Then I can consider intersection of such guys. It will be an analog of complete intersection of algebraic geometry. So you get some subvarieties. You can consider intersection of those. But then I consider, I'll be just a little bit, what's called sheaf of semi-rings on this idempotent semi-rings. Namely, what we restrict, it will be restrictions, it will be some real valued functions on such intersections, which are restrictions of convex functions. So consider various restrictions. Convex functions can add and take maximum. And then you say, like in algebraic geometry, what is a variety? It's something with a sheaf of ring which locally looks like this. Now to the sheaf of semi-rings. Yeah, that's this word that algebraic variety depends kind of meromorphically algebraically on a small parameter. It's actually closely related to non-Archimedean geometry. It's so-called Berkovich spectrum. So what is non-Archimedean geometry? You should have some field instead of complex numbers, like p-adic numbers, with some norm which satisfies non-Archimedean triangle inequality. Not some usual triangle inequality is norm of x plus y, norm x plus norm y. It's usual triangle inequality. And the basic example of a field is complex or real numbers. And we have analysis, we have kind of geometric intuition for varieties of field numbers. And if you have non-Archimedean field, then this Berkovich spectrum is replacement of usual kind of underlying topological space in complex geometry. And it's kind of tropical variety. Strictly speaking, some projective limit, but that's how this from in non-Archimedean geometry varieties look like. And when you have parameter going to 0, then you have non-Archimedean field like Laurent power series. So you consider all possible which series in positive and negative powers of variable t, but which terminates in negative direction. And you take and you say that the norm of the things, it will be equal to let's say 10 to power k0, and ak0 is non-zero, the leading coefficients. Yeah, so this depends on, and I think depending on small parameters, it's algebraically it's being variety defined over this field. So it means the coefficients of the equations belong to this field. Yeah, so what I said here, it was some kind of definition which I proposed to you. And tropical varieties, they're a very singular object from naive point of view. There are kind of pieces of linear spaces, and then there are singularities. And then on pieces of linear spaces, this looks like a domain in coordinate space. And what are coordinate changes are integral affine transformations. Just in two variables, you consider transformation depending on 6 integer parameters, then A, B, C, D is 2 by 2 matrix with determinant 1, and similar in higher dimensions. And these things which really appears in real life. I've considered sunflower. You see that in any kind of small domain, it looks like you just a little bit stretch your picture. You get usual square lattice. You get kind of coordinates for the seeds. You can put what are coordinates for the seed in sunflower. But it's not really well defined, because if you follow around, you get this famous linear transformation, which is closely related to Fibonacci numbers. And it's explained why, if you consider sunflower, count how many kind of spirals going left and how many spirals going right, you get two next to each other Fibonacci numbers. Which I didn't count how many here. I think it's something like 21 and 34 in this picture. Yeah, the same thing is right in pine trees. Yes, it's. In fact, it's a very interesting question. What's really going on? And we have some biologists in HS, and I'm working here, specialists in plants, and ask him the following question: if consider cells of any living organism, then the set of cells forms of some trees, of some tree, because cells divide and sometimes die; they never converge. So you say this, you introduce subsets in the set of cells which exist in a given time, which are daughters of certain cell in the past. So I get a collection of sets which either intersect or contain one another. And there is a question for this Fibonacci-like picture: decomposition of the set of seeds into subsets. I really have no idea. And one can actually accept that it's not really well-posed question, because the seed is not a cell. It's extremely complicated thing as well, but one kind of formulate in seed something kernel. It looks kind of highly improbable that if you these details in this process will give non-overlapping, some kind of overlapping clusters. Yeah, but it's a really good question, and it's very hard to study it by microscope. What is really going on? What is this? Yeah, so it's a good question in between mathematics and plant biology. Yeah, and the tropical geometry, it's extremely important role in mirror symmetry, which is subject of the workshop, which is now going on. So, what is the story? So it will start your kind of standard song in string theory. That space-time should be 10 dimensional. Yeah, not a seem to understand. Yeah, but the real world is 4-dimensional, so we have some discrepancy. So it should be kind of 6 dimensions, should be very small and invisible, and we should interpret if string theory have anything to do with real world, which seems to be the case, that this 10-dimensional manifold is a product of 4-dimensional space-time and some small 6-dimensional manifold with vanishing Ricci curvature. And in fact, it's because of supersymmetry, it's not just vanishing Ricci curvature, it's a complex algebraic 3-dimensional variety. Algebraic in the sense kind of by chance, it's not, it's scalar variety, but under reasonable assumptions, it has to be algebraic. It's called Calabi-Yau variety. Yeah, so it has metric which is scalar metric on this complex manifold, and with Ricci curvature 0, and this famous Yau theorem, solution of Calabi conjecture, which kind of describes what are parameters of this matrix. It didn't describe what is a metric. It's kind of say what it depends on. And there are parameters of complex structure and parameters of Keller class, completely independent parameters. And it's also a very important result in this business, Tian-Todorov theorem, that complex parameters of Calabi-Yau variety are unabstracted. So you get kind of smooth manifold of some parameter space of this manifolds. With Keller parameters are unabstracted, it's completely obvious because it's some kind of domain in second cohomology. And what mirror symmetry does, it interchanges these two groups of parameters for two different manifolds, which leads to the same physical theory. In fact, if one analyze what string theory wants to say, there shouldn't be no 6-dimensional manifold at all. It's kind of illusion. The people want to construct to use instead of 6-dimensional manifolds some conformal field theory in 2 dimensions. And it's not clear how to construct the series. This Calabi-Yau varieties, it's one way to construct the series, but there are other ways. And definitely there are series which has no geometric meaning at all. Yeah, so that it was some kind of physicists look on Calabi-Yau manifolds because it's kind of simplest source of what they want, but there are other stuff and nobody knows how many of them. Yeah, and so originally when string theory started, people thought that very few such things, and they have only one example essentially in mind, and they said that if you just arrange these parameters, then you get standard model or whatever. But and the simplest example which people studied, it's if you look at the Finnish Calabi variety, it's a Quintic threefold. So you consider four-dimensional projective space and write a given by equation degree 5. But because it's a projective space, it's projectization of five-dimensional vector space, so you get equation of degree 5 in 5 complex variables. And that's a general rule. To get your hypersurface in projective space, you get degree of equation should coincide with number of variables. And this particular Calabi depends on 101 complex parameters and one Keller parameter. And it has some mirror dual Calabi variety, which is a bit hard to describe. You take some special family of Quintic varieties, which has big symmetry by groups of order 125, divide by the group and resolve singularities. And the mirror dual variety has only one free complex parameter equations and has 101 Keller parameters. And mirror symmetry concerns actually not just two dual varieties, but both varieties should simultaneously degenerate. It depends on small parameter, or maybe several small parameters, and degenerating in a maximal possible way. So there are many good ways to say, many equivalent definition. What is the maximal possible manner? Just for special is that the monodromy in the middle cohomology should have a Jordan block of size, maximum size. Yeah, mirror symmetry also does concern not necessarily three-dimensional Calabi varieties. It could be anything in any dimension. So this origin in string theory are not really relevant here. But let's reduce to this example. So in example, so this Quintic and threefold and dual threefold, you get two varieties which depends on parameters, one on 100 and another on 101, and they degenerate in some way. You get some tropical varieties by kind of general philosophy of real dimension 3. And mirror symmetry, in fact, is nothing but some kind of duality between tropical varieties. And what we see for kind of actual complex varieties, it's some kind of small deformation with it, but the basic thing is duality between tropical varieties. And one can develop kind of limit of physics. For example, this equations that Ricci curvature is vanishing. One can formulate some equation for metrics on tropical varieties. And the equation is really very beautiful one. It's called real Monge-Ampere equation. So you get these domains in Rn. Let's say Rn, okay. N equals 3 Calabi, open domain. And the equation is the following. You want to find some function, h, commutative to R. It should be convex function. And such that if you consider determinant of the matrix of second derivatives, then you get, at every point you get 1. So you get, this is the Monge-Ampere equation. And then you can make Legendre transform. Okay. If you get a convex function, then you can have kind of dual function. Here it will be scalar product of two vectors. And it's again convex function defined somewhere because it's attained in the interior of the domain, and then it's again satisfying the same equation. It's actually easy to see, and it was known to Monge, I think, this duality, so creator of Monge-Ampere equation. Yeah, so it's in a sense nothing new in this world. Yeah, so this, and this is basically a duality between tropical Calabi-Yau varieties. And now I want to finish my talk with kind of true picture of Quintic threefold. If you look on some popular book on string theory, so Scientific American, then you see some kind of, again, negative curvature kind of surfaces, kind of very non-convex one, multicolored, and I have really no idea what is it. Yeah, it cannot be Calabi-Yau variety because Calabi-Yau variety it's three-dimensional, but what you see in the pictures that's but even three-dimensional, it's complex three-dimensional, so it's at 6 dimensions, and my imagination already stops much earlier. Yeah, so yeah, I think it's again some kind of public relation, whatever things people don't know what to draw. Yeah, and maybe they see some kind of ramification to some projection. Yeah, I don't know. It's completely nonsensical pictures, I have to say, just trying to impress public. Now I want to give kind of more more reasonable picture what is really going on. Just for case of Quintic threefold. So the construction goes in 2 steps. So the first step, you choose 4 points in usual Euclidean 3-dimensional space, and then kind of generically get 4 points, and then you choose the 5th point inside the tetrahedron spanned by the first 4 points. You get 5 points. Now you connect by intervals all these 5 points. You get 10 intervals, and also get 10 triangles. And these triangles do not intersect each other, which is very important. Yeah, so they only touch along edges. Okay. What is step 2? In each triangle, we draw a picture which is already familiar from what I draw. Just it's now equation of degree 5, and you can see the planar quintic. And if you don't remember what is the genus of the quintic, you can count. It will be genus 6. Yeah, so it's so you get these curves, tropical curves of degrees of genus 6. What these pictures, and what you do? And you just draw together, and if you need a little bit of imagination, just you see that on this graph, each inner vertex have 3 edges, so it's get a graph of degree 3. But then there are boundary points, and these boundary points will also have degree 3 because each edge here belongs to 3 triangles. Yeah, so you get graph of degree 3. Each vertex has degree 3. And you get graph in 3-dimensional space with 200 vertices. Oh, sorry, it's I have some mistake. If degree 3, sorry. And 300 edges, yeah. So you get this huge graph. Maybe you should add 1 point at infinity to get, say, a 3-dimensional sphere minus and the graph in this sphere. And this graph is the locus of singularities of the integral affine structure on 2 tropical varieties, which are mirror dual to each other. associative degenerate Quintic threefold and degenerate Calabi threefolds. And this is kind of real picture. One maybe should say kind of more specifically what is a affine structure, kind of seed flower picture, roughly speaking, outside of the seeds, kind of many kind of things. And that's the right picture of Calabi threefold. You can see kind of topology, geometry, and that's it. Yeah, there is a even simpler situation which one can study. Why to go to 3 dimensions? One can go to 2 dimensions, even to 1 dimension. But 1 dimension is a bit too simple. In 2 dimensions, two-dimensional Calabi-Yau, it's called case resurface. It's again one of typical mathematical name tags. There are several theories what it could mean. It could be, yeah. There's some peak in Himalaya and so on, yeah. But case resurface is given. Consider, for example, surface sitting in CP3, hypersurface of degree 4, quartic hypersurface. And then the corresponding, yeah, it's famous toy of algebraic geometers. And from this picture, this tropical picture, tropical case 3, it's 2-dimensional sphere. But on this sphere you get 24 points. There's a singularity of a affine structure. Of integer affine structure. And near each singularity, you know how this picture looks like. You consider plane with coordinates x and y, but you remove some angle sector from here, like vertical axis and diagonal. And you glue points on near kind of neighborhood of this angle sectors by transformation x, y goes to x plus y comma y. That's a basic transformation. One can draw kind of picture of integer points here, and so one get kind of some nice like sunflower picture of integer points around this 24 points. And moreover, the whole thing, you will have a metric, it's Calabi-Yau metric. The Calabi-Yau metric in this case one can write explicitly, and this metric will have positive curvatures by I think the theorem of Alexandrov, that one can make actually convex body in R3. Such induced metric is exactly this Calabi-Yau metric. So it means that you can really made it from wood or whatever, and then it will be your pocket model. Maybe just draw a little bit integer points. This will have 24 singular points and many integer points, and that will be your pocket model of case resurface, from which you can see again all topology and the whole thing. And there are really a lot of fun here, even with this 24-dimensional case. For example, each of this ramification points, this point when you have the singularity could be actually not point 0, but point just like on horizontal axis. It could be any point here. And then I get this 24 points. And each of these points is endowed with some kind of natural tangent direction. And then there was a picture which we developed with Jan Söbelman many years ago that one can imagine that this point kind of singularity moves. You kind of write the same formula, but as a new singularity point. And in a sense, it will be the same tropical variety. It will be, strictly speaking, the same non-Archimedean space, or the same Berkovich spectrum, which projects differently to a sphere. And I get different singularity points and projections. Yeah, so I get 24-dimensional parameter space of such spheres. And this space is it's a very mysterious space. Some part of the space we understand, something of codimension 6. When you get explicit metrics, one can understand completely. There is a picture that for this piece which understand completely, we know fundamental group. It's something like SO, 18. And then this with integer coefficients, and then this fundamental group, if you think about it carefully, will act on two-dimensional sphere by piecewise linear homeomorphisms. Yeah, so the conclusion will be that some kind of group SO118Z, maybe 17, I don't know, I forgot which is exactly, start to permute seeds in my sunflower. And how many seeds? It's up to you. Actually, the simplest example is act by symmetric group of n square plus 2 elements when n is arbitrary integer. Yeah, so you get something absolutely fantastic from point of view of arithmetic groups. You get some kind of to many symmetric groups, presumably epimorphically, and kind of two conjectural description of the section, two description of the section, and conjecture that the description coincide. Yeah, but that's only for part of this parameter space which come directly from algebraic geometry. But then it has a larger space, 24-dimensional space. And with my student Dima Panov, we proved that this parameter space is a Hausdorff manifold. So we get 24-dimensional manifold. Yes, and fundamental group has something to do with this SO118. So you get some 24-dimensional manifold. And what it could be good for? There was so my conjecture is related to monster. Namely, for monster group, you have infinite sequence of representations whose dimensions are coefficients of modulo. And then Hirzebruch, long time ago, conjectured that the sequence of dimensions will be the same as should look like elliptic genera of certain 24-dimensional manifold. So it should be some pretty unique 24-dimensional manifold. And why monster group acts on these spaces? The idea is this monster should act on this 24-dimensional manifold. So it should get a quotient, get 24-dimensional orbifold. And these spaces are harmonic spin kind of solution of d-bar equation, symmetric power of some bundle. Yeah. So the goal is to construct some kind of interesting 24-dimensional manifolds. It's still open, and with fundamental group monster. And now we have 24-dimensional manifold naturally coming from nothing. Its fundamental group has something to do with this. I think monster group also has something to do with the same group. Yeah, and dimension match. So my natural guess is you should a little bit compactify the things, go to limits, and then I get the manifolds whose fundamental group will be monster. Yeah, so that's my monstrous idea, and thank you.
Any questions, any comments?
Yeah. 25? No, monster. No, monster. It's only to this. Yeah, related. Yeah.
the generating function or something you are looking at?
Yeah, it should be the index of Dirac operator on some natural bundles, on symmetric power of tangent bundle. Yeah, it should be spin many. Yeah.
That should be something like a J function.
Yes, exactly. Yeah, exactly this series from once. Yeah. Sorry? Yes, symmetrics, yeah. Yeah, no. There are semirings which are not idempotent, like positive numbers with usual addition and multiplication. Yeah. Idempotent is kind of limit. Yeah. Yes. It's moduli space of integral affine structures such that monodromia belongs to SL to Z square. When holonomy belongs to this group, the moduli space is 24-dimensional manifold. Yeah. Maybe orbifold.
More questions? Comments?
Yeah.
We have some variations in the periodic one.
Yeah. Yeah. If you have variety over periodic numbers, and it doesn't have a good model, it has kind of bad model, then you get this tropical stuff again. Yeah. And in fact, it seems that one can develop mirror symmetry over varieties of a non-Archimedean field and have kind of Foucault categories and so on.
Something speak again.